Hello everyone, welcome back in this subject strength of material. Myself, Dr. Ishad Ahmad Khan, working as Associate Professor in Department of Mechanical Engineering, Sagar Institute of Research and Technology, Bhopal. Today topic is elongation due to self-weight. And uh, in the last class, we had discussed about the elongation due to the when we are applying the external load. And today topic is elongation due to cell weight. So in class, in this lecture, mm, that we discuss here the elongation in rectangular bar section or elongation in conical section due to cell weight. Let's take first one, the elongation in rectangular section. And you can also say that prismatic section. So let's consider a rectangular ball which is freely hanging and its own weight you can see with in this diagram. And to solve to get a relation or elongation um, due to cell weight, so we take first a small section of length del x, which is located at a distance x from the free end. Let's take some another variables, that is area of cross section of bar, here shown by a, and L is the length of the bar, and small w, that is weight per unit volume of the bar, and this is also called as the specific weight of the bar. And the weight of the bar is denoted by capital W, and we can write small WAL, and WX is the weight of the bar below the small section. And it can also write as, you can see that we can write this also, the small w into the cross-sectional area, same for whole bar, and the length till this. So this is called a x. So we can write like this. So let's write the elongation of small length, and this is written with the this relation what we have discussed already. Elongation in bar, when you apply it, the external load, where P is the external load, L is the length of that bar, A is the cross section, is the Young modulus of that material. So we have just analog with this. So here P is the external load, but here Wx is the weight of the bar below the small length. So this Wx and del x, it is the del x is simply the length of the small section. So here P is the length of the bar. Here we are calculating the we are finding the elongation in the small section. So as we can write like this upon A is here also. So just put the Wx value from here. You can see W x and del x upon A. And A, let's erase all these values. Okay. So move to the next slide here. So now we have calculated the elongation at a small section, and to get the elongation of the whole bar, we have to integrate from 0 to L. So we can say the elongation in the whole bar equal to simply that previous relation, Wx upon E. A is cancel out because both are the numerator and denominator, so it is cancel out. So we can integrate this. So small w upon E is the constant value, and x will integrate with respect to x. So x square by 2, L to L just puts the upper limit and lower limit, and this is the relation WL square upon 2A. And this W can be written as WAL into L. Okay, and this A can this A it, we put by putting at numerator and denominator both sides, in a numerator and denominator. So this can be written as this can be written as capital W, weight of the whole bar. So the final relation is WL upon 2AE. Okay, so we can conclude it from here. The elongation of the bar under its own weight is equal to the half deformation or elongation due to direct load equal to weight of the body applied at the lower rate. So you can say, so that elongation due to self weight, it is half of the direct load if you apply it at the lower end of the bar, which is equal to the weight of the bar. Okay, so this is a simple this is simple relation elongation due to self void. If your bar is in shape of rectangular, can say prismatic or circular. For the circular bar also, this can be applicable. So this relation we can directly use to calculate the elongation due to self weight. Hope you got this concept. So let's discuss second case. So in second case, that is conical section. Same, the process is the same. You can we have discussed for the rectangular section. So let's see similarly area of cross section of a small length, that is a small length we have taken here, that one, and this area of cross section which is located here, that is A, because here the cross sectional areas vary because this is the conical section. So is in this part at the above the small section, the which area cross section is A, and L is the length of the conical bar, and similarly small w is the weight per unit volume of the bar. W is the weight of the bar below the small section. So we can say there, this is the conical section, so that's why we can write the volume of the conic is 1 by 3, and the cross section and the height of the cone. So that's why it can be written as AX. Cross section is how much? A, and height is X and by 3. So this part is a volume of the cone, and this is the specific weight. Okay, so just multiply by this, so we get the weight below the section, small section. So similarly, we can write here elongation in small section Wx del x, and just put the value of this Wxa into x by 3ae, and this is for a small section, and if you want to no elongation in the whole bar, so we have to integrate from 0 to L of this relation. So what happened? You can see this A cancel out, and we can write Wx upon 3e till x. So W small w3 is, it is a constant, and just you integrate it small this x, so it's become x square by 2, and put the upper and lower limits. So final relation is WL square upon 6e. So this relation elongation due to self weight in the conical bar is small WL square upon 6e, where small w, you know that weight per unit volume of the bar, that you can also say the specific weight of the bar. So thank you so much for listening this lecture, and soon we will meet in the coming lecture.